This is a brief introduction of the index test box steady-state algorithm that dramatically reduces the labor and expense of acquiring the field data necessary for hydroelectric turbine optimization. Data collection method. The data for this demonstration was collected using the normal power plant instrumentation and station data logger at a run-of-the-river power plant with 3 18-megawatt Kaplan-type bulb turbines. Existing power plant instrumentation and data logger were used to acquire the data. No new equipment was purchased to facilitate and set up the data acquisition functions. The governor manufacturer and power plant personnel made all of the software changes to the turbine generator control and data acquisition systems. Setup was accomplished by making minor modifications to the software in the 3 governor PLCs, the human machine interfaces, or HMI, and the station data logger located in the power plant control room. Data processing method. The data logger runs 24/7, continuously recording data into memory. The data in memory is downloaded onto a thumb drive every few weeks and sent to actuation test equipment for analysis. These data files are copied to the hard drive on the index test box computer in the normal manner for data files on any IBM PC type computer. The index test box post-processor data analysis program is used to glean the steady-state points from the data. The steady-state points are sorted for common head, gate, and blade offset values, and then plotted in Cartesian coordinate graphs in the commonly accepted formats. Definition of the new 3D cam surface is then accomplished in the conventional manner. Description of the index test box. An index test box is an IBM PC computer with the patented, copyrighted, index test box turbine data analysis software running on it. The current configuration of the index test box is running on a Hewlett-Packard all-in-one touchscreen PC computer. The main display screen controls the analysis of the data displayed in a real-time strip chart format, and a second monitor displays analysis results as a 2-dimensional representation of the 3D CAM data profile. Using the OPC communication network and the Internet, the index test box could also be located remotely, in the power plant control room or in a more removed location hundreds of miles away. The index test box program, written in Visual Basic 6 software language, resides as a group of files in a folder on the hard drive of the computer, just like any other Microsoft Windows compatible software program. This list of files is 2 months of data from the Clerg data logger. Clicking on a file name loads a 2-hour block of the file on disk into the index test box RAM memory for the steady-state analysis. From upper left to lower right, the parameters shown are operating head, gate stroke and blade angle, both in percent, flow in cubic meters per second, and generated power in megawatts for Unit 1. The other 2 units are arranged in the same way, Unit 2 and Unit 3. These are followed by the total flow and total generated power for the entire plant. The control panel in the upper right corner selects which data files to analyze, size of the sliding window, which display flags to show, resets counters, and starts and stops the analysis. Located below the control panel is the preset limits table for the steady-state algorithm. Each strip chart display panel on the left side has a corresponding average value, standard deviation, and slope limit value displayed in the limits table. The 1,000 sample wide sliding window is 8.3 minutes long and is signified by the blue, mostly horizontal lines that rock their way across the strip chart displays from left to right. The window moves across the 2-hour block of data, taking steps of 100 samples. At each step, the steady-state algorithm performs a linear least square fit to draw a best fit line through the center of mass of the data in each 1,000 sample parse, the results of which are an average value and slope of the line. A second pass calculation of the square root of the sum of the squares, or RSS, derives a standard deviation value to quantify the noise between the measured data points and the best fit line. A data point is deemed steady state if the slope and standard deviation values are less than the predefined limits values in the table. A vertical green line is drawn through all of the strip chart panels to show that a steady state point has been detected. The vertical axis of each of the strip chart displays is automatically scaled to fit the range of the data in the 2-hour block for that parameter. 3D CAM surfaces use two-dimensional Cartesian coordinates to display three-dimensional data. The x-axis across the bottom is gate stroke in percent. The y-axis on the left side is blade angle in percent. The y-axis on the right side is relative efficiency in percent. Blade curves are theoretically projected beyond the physical limitations of the machine to provide an orderly transition at 15% and 100% blade, the end of travel of the on-cam lines. The third dimension of head, or water level across the turbine, is expressed as a number of curves plotted in 2 dimensions. This first curve shows the optimum or best blade to head and gate profile at 4.5 meters water pressure across the dam. For these bulb units, this is defined at 5 head levels: 4.5 meters, 5.3 meters, 6.2 meters, 6.8 meters, and 7.4 meters. Now let's put this into the context of a bulb turbine with a Kaplan runner. The cross-section of the civil works in a 7.5 meter high dam shows a Kaplan bulb turbine and the water passageways constructed to direct the river's flow through the turbines. Although a measurable efficiency decrease is caused by trash racks and stop logs, you've still got to have them. A differential pressure transducer across the trash rack monitors this loss, and an alarm notifies the operators if the trash rack clogs with debris. Operating head is measured as the differential pressure from just in front of the bulb to the discharge tail race. Operating head differential pressure and gate stroke are inputs to the 3D CAM. The output is the blade angle set point. Flow is measured with a pitot tube flow meter. The pitot probe sticks out into the large cross-section area in front of the turbine, and the reference tap is located just in front of the gates. The decreasing cross-section area in the flow conduit requires that the water is accelerated as it passes around the body of the bulb. So the pitot tube flow meter is actually measuring the force that is accelerating the water through the turbine. Head and tail water levels are measured as PSIA using single-ended absolute pressure transducers. Along with gates and blades, all of these pressures are recorded by the data logger every 1/2 second for later post-processor analysis. Analysis consists of gleaning the steady-state data points out of the continuous measurement streams captured by the data logger, sorting the steady-state data points by head, gate, blade, and power, and then charting the sorted steady-state data points in the conventional manner. Canned data. The index test box steady-state analysis works with both live and canned data. This example is using canned or pre-recorded data. Modern power plants have excellent instrumentation and data loggers. With a few software modifications, the vast majority of power plants will be capable of providing turbine optimization data already. We can make any necessary programming changes, or they can be done by the power plant personnel or the turbine control system vendor. How the canned data method works. The steady-state algorithm captures data points whenever all 3 of the units are standing still. The 2 months of off-cam data we have yields thousands and thousands of steady-state points. The sorting process for steady-state points takes 2 passes. When the program resets, it creates the folder structure to store the steady-state data points in. The data is sorted for analysis using the traditional constant blade and constant gate methods, or the new constant power or random scatter techniques. The first pass sorts the steady-state points by head and blade angle, head and gate stroke, and head and power, and stores them into the appropriately named folders with file names that identify the contents. The second sorting process uses another Visual Basic program. This demonstration will use the constant blade test, which is the most common method for Kaplan turbines. For greater simplicity, our method uses gate stroke as the x-axis. This doesn't make a great difference because Kaplan turbine suppliers strive to get gate opening and generated power to come out proportional and linear with gate stroke. The steady-state algorithm has gleaned over 7,300 steady-state points from the 2 months of off-cam data. The second sorting program opens each of these files and sorts the steady-state points contained in them according to their blade offset values. A minimum of 2 data points at 2 or more offset values are required in order to pass this second sorting test. Analysis of the data is performed in Microsoft Excel. Procedures and techniques will be presented in another video. 3D CAM demonstration. The final topic for this video, and the first topic for the next one, is the Index Test Box Kaplan 3D CAM demonstrator. This utility displays 4 y-axes of blade angle in percent, flow in cubic feet or meters per second, power in megawatts, and relative efficiency in percent, all plotted versus skate stroke in percent as the x-axis. This animation was created to clarify exactly how the blades move relative to the 3D CAM data profile. Getting the right contour for the 3D CAM profile is only half of the job. The hard part of it is to get the new optimized cam surface profile into the machine and verify accurate and robust blade positioning using Index Test Box's diagnostic features and tools.